Welcome to our live Q&A session. Let me introduce our chair. Professor Rajesh Sundaresan is professor in the Department of ECE in ISC Bangalore. His research interests include information theory, communication, control, and computation over networks. So Rajesh, take it over.
So first of all, let me begin with a thanks to Muriel for her very clear lectures. So we have some questions in this session. I'm not sure whether Adrish has shared them with you already.
He has. So I have them open and I can go over them, and then I'm happy to take questions live from the audience.
Okay, all right. Yeah, so maybe we can begin, perhaps if there is a question from the audience live, just to get things started, we can begin with a question from the audience and then we can go through the questions that we received. So someone from the audience like to pose a question?
People might be a little shy, so maybe I can just share the questions and that might actually generate more questions, I think.
There is a question. I will bring that person to the stage. One minute. There is a question.
I thought it might be a good idea to begin with an interactive question first. And then
1 minute. I'll bring that gentleman to the stage. Yeah.
Sure.
Switch on your camera and then you will be live. You can ask the question directly.
I guess it's Shahid is asking, is that right?
I think let's go with the questions I sent and then we'll see. Yeah.
Right.
Yeah, that's okay, fantastic. So I see it's on the chat. There's something on the chat maybe. Not able to turn on mic. Okay, so Shahid, why don't you let me answer some of the questions that were preloaded, and why don't you go ahead and type your question in the chat and I'll grab it from the chat, okay? So let me go ahead and take some of the questions that were sent. Thank you for those. So let me start with the questions for lecture 1. So the first question is, could you give some insight in what it means for entropy to be infinite? It's just a statistic. So if we have any finite channel, you can't have anyway an entropy that's any finite alphabet channel. So in the example that I gave in say binary, then the entropy would always be upper bounded by the cardinality of the size of the channel. So if it's binary 2, then you would raise it to the length of your string. So it would be 2 to the n, and then you would take the log of that to get the entropy. So n log 2 would be the maximum entropy for any binary variable where you're looking at vectors of length n. Okay, so of course, if n were to get bigger, then that would go to infinity, but it would just go to infinity because you're in effect getting a longer and longer vector that has more and more stuff going on. So it would be just like any statistic, like the average or the variance would also go to infinity because you're just looking at a longer and longer vector. So there's nothing magical there. So I hope that answers that question. The next one is, what is the meaning of variance of entropy is finite? Entropy is a deterministic quantity. Okay, so that's a good question. So actually what we're talking about is you're taking the expectation. So think of minus log of the probability as being itself a random variable, right? So I'd like you to think of entropy as the expectation of a random variable, which is minus log of p of x. I don't know if I can share. Is there any way for me to write like in Zoom? I guess maybe not, but maybe I can write here on the chat. Can everybody see the chat? Yes? So think of p sub x of x sub I as being a random variable. Okay? Which means that I have a random variable that takes value p sub x of x sub I with probability P sub X of, okay? So the sample here of minus log of, sorry, that's not what I meant. So, so that's what you usually have.
There is a
Minus-
whiteboard option if you'd like to try that.
Pardon?
Whiteboard, there's a whiteboard option, and also you can share the screen. So you can write in your tab and just share the
Yeah.
screen.
Where's the whiteboard option? Sorry.
More, and then whiteboard.
Sorry. Where's the more? More.
The three
All
dots.
right. Oh, we're cooking. Great. With gas. All right. So let me see how I do with this one because it's a little small. Okay. Yeah. No. Sorry. Not happening. All right. Sorry. So now let me look at the sound. So now let me look at the phone. So the RV P of xi is being a random variable. That's what we're used to. Now I'm going to look at an alternate random variable. So it's not a random variable that takes sample value minus log of P of x xi with probability P sub x of xi. Okay. So you see what I've done here is like I started, there's nothing on the whiteboard. I'm not having any luck using it, shade. So just read on the chat. Sorry, I'm just going to be typing in the chat. So the RV takes the sample value minus log of P of x sub xi with probably P of xi. So see, the original one was it takes value xi. So the original takes value x sub I with probability P sub x of x sub I. And now the new one it's a random variable. It takes value minus log of P of xi with probability P x sub I. Now the entropy H of x is the expected value of the new RV that takes this sample value minus log P of xi. And that random variable is the one that has finite variance. Okay, so the random variable that has finite variance is this one that takes value minus log P sub x of xi. Okay, and that's where the finite variance comes in. We call that sometimes the sample entropy. Okay, so when we talk about entropy, we're usually talking about this mean already, but there is a random variable, which is the sample entropy, which takes this value minus log P of xi, and that random variable has finite variance. Okay, very good question. Let me now move on to the questions from lecture 2.
Maybe I can read it for you, Muriel.
Sure. That's okay. I have them right here, so I can read them out. Thank you. Lecture 2. Isn't noise-centric ML decoding more difficult than code-centric ML decoding for practical channels? If noise is Gaussian. Okay, very good. So come to the last lecture because the answer is no. Okay, it's a very surprising answer, but basically, you remember that's why I made a big deal about the fact that we're not really guessing the noise, because you're right. If the noise were continuous, you'd have to guess all kinds of possibilities. You're really only guessing the noise effect, and even if the noise is continuous, the effect of the noise is not. So, not the next lecture. The next lecture is going to go a little bit more deeply into the mathematics. But the last lecture is going to go into grand soft information. Soft information is the case where you have this a representation of the continuous nature of the noise, the continuous nature of the channel effect, and you will see there that actually that we can decode. And actually, there are already proposals for implementations. People have already made architectures for chip implementations. So no, it's still significantly easier than decoding based on the code. And at the same time, it's of course universal. And it shows, you will see when you come to that lecture, that rather than having to mess around with doing all kinds of complicated codes, pretty much all codes are good, except for a few codes that are junky. All codes are good as long as you decode correctly using GRAND for maximum likelihood decoder. So it's a great question. Stay tuned. That will be answered
may I
2
add a
lectures from now.
question? May I add a
Sure,
question?
of course, of course.
So is it connected to maybe quantizing the noise and then guessing the quantized noise in some way?
It's actually much easier than that. That was our original, that's a really good question, Rajesh, because that was very much what originally we thought would happen. But you don't really need to do that because you only care about noise that will change your decision, right? So, you could quantize the noise and look at 2 different noise effects, but they wouldn't actually change anything. So why do you care, right? Because in the end, it's a little funny. We're starting with guessing the noise, but really we're guessing the noise effect. So it's not so much about quantizing the noise and guessing the quantized noise of that, because then what would happen is the complexity would go up with the level of quantization, and you might be quantizing around areas of noise that you don't really care about because they didn't lead to a change, right? It's more about figuring out which bits are more likely to be flipped or not.
Okay.
So it's more about the likelihood that the noise caused a flip or not, rather than exactly what did the noise do. That's a very good question. I did want to actually point something out for people who have an interest in doing a little bit of further reading. I should have popped this earlier, but please do go and check out. I'm going to pop it in the chat. Please go and check out this website, which has all the papers that you may want to read if you want to read more about this. And if you're interested in the continuous version of the noise, I would urge you to read the S-GRAND paper, soft GRAND, and also the orb GRAND paper. Those 2 papers deal with soft GRAND, gives you a full soft information use. So this is actually maximum likelihood decoding in Gaussian noise universal decoder. So up until now, it was not something anybody knew how to do. So now we can do it. And you can just follow it. It's got a tree structure. It's not a tree structure, it's a heap structure. Come to the last lecture, I will overview that. I'm glad that people are interested. I had put it as an optional lecture, but by all means, come to the last lecture. The next lecture is it's a bit more mathematical. It's optional. Okay, but these are good questions. The second question is, can you please explain, say, with an example of AWGN channels, how would you guess noise? This is very related to the first question. So again, come to S-GRAND and I will show you exactly how to do that. Third, the decoding is critically dependent on the noise statistics. Noise statistics is something we periodically estimate. What effect does the estimation error of noise statistics have on the performance of the decoding algorithm? That's also a very good question. We'll show you how noise statistics, such as Markov order, we can actually use the noise statistics to avoid having to do interleaving, and that actually leads to much better guessing. So the usual noise model that we assume in encoding and decoding of ID noise realizations is actually a worst case for guessing, because you're going to, any lack of structure will lead to a longer guessing. I hinted at this a little bit when we looked at the in the second lecture at the curves for how long it took to guess. I showed you with ID noise and I showed you with a noise that had a Markov structure. And I showed you the Markov structure takes a little less time. And of course, as the noise gets more memory, whether it's memory in time, space, I don't care. Actually, the guessing gets faster because there's more structure in the noise. As to the mismatch between the noise, the guessing, and the guessing and the statistics, we actually have some work on mismatch guessing. And it turns out that, of course, guessing within any tilt of the original distribution actually doesn't change the order of the guessing. So for instance, you could have somewhat different noise statistics, but they don't really change the order of the guessing. We do have some papers on mismatch guessing. I would very much encourage you to look at those. And those will give you answers to that very good third question.
I have another add-on question to that, Muriel.
Yes, of course.
When you look at additive noise channels, and you can use the Gaussian decoder even when the channel is not Gaussian, and you can get achievable rates at the Gaussian rate. In some sense, Gaussian is the worst case channel for a given variance.
It is.
And additionally, you can use the Gaussian decoder and achieve that particular rate, which is the Gaussian's rate. Is there a similar thing? Can you assume Gaussian channel and guess the noise according to that, and would that yield similar performance in this case as well?
So we have mathematical results on what happens when you guess with the wrong statistics, I think that, again, one of the things to remember a little bit on the guessing when you have a continuous noise is that we're not guessing the noise itself. So the results that we have obtained empirically are very good, but I think that what you're proposing, Rajesh, would be a really interesting search, which would be to say the noise is not Gaussian. I'm guessing the noise effect, again, because remember, I'm not guessing the noise, I'm guessing the noise effect as though it were Gaussian, how far off I am. I think that's a really excellent question of actually having some results there, because we know the effect of guessing a sequence with the incorrect statistics, and we know that in some cases it makes no difference or it makes little difference. It's pretty robust. And we know that we're not actually guessing the noise, we're guessing the noise effect, right? Afterwards, of course, you could reconstruct the noise because, and that is actually what we do in noise recycling, which we're not covering in this class, because you can remove, once you've decoded correctly, you could remove that code word and, the modulated version of the code word and just get the noise. But generally, you didn't actually care about the noise. So you could use this to guess the noise, right? But we're not guessing on the noise directly. So what would happen is if you were guessing the noise effect but had incorrect statistics, I think that's interesting. I would definitely encourage you to look at Ken's paper on Old-Grant. If you're interested in looking at this, that's definitely the right paper to work off of.
Thank you.
But that's a great question. Question 4, we're decoding the grant. How are you checking that yn minus zn is a code word among the 10 to 277 strings? Yes, so if you recall, one of the steps in there was that the code does not need to, that arbitrary 2 to 77 strings of checking. That was something that would be if you applied naively the 1948 Shannon paper. We are looking at codes which are easy to check because they're linear. Even though they may be random, they're random linear. You could also have some nonlinear codes, but then, again, the description of the code is short and you're using the code only as a hash to just check whether something is in there or not. If you come to the last lecture, you'll see that we can use CRCs. CRCs, cyclic redundancy checks, are just a hash, and those turn out to be fantastic codes. They actually perform as well as CRC-aided polar codes. So actually the polar codes by themselves, you see, don't do well. The CRC-aided codes do well, but it's because of the CRC, because you could actually replace the whole code with just a CRC, and it does great. So you have a code that is easy to check. So that the whole aspect of the random code construction is not the only part that's useful about it. That is the lack of structure. You can achieve that lack of structure with a random linear code or with another random code construction that might not be linear. So that's a good question. I hope that answers that question. Going on to question 5. Please explain the meaning of unlikely noise sequence dominate in the slides. Yes, so actually, I will explain that in this next lecture on the more mathematical aspects, but just to give you a little bit of an understanding. When we're doing the guessing, we can stop basically after we've done guessing that already covers the 2 to the nh most likely sequences. The 2 to the nh most likely sequences have a probability that goes to 1. A way to think about it is because of the 2 to the nh most likely, they naturally dominate in probability the typical set, and the typical set has itself 2 to the nh sequences and has itself a probability that goes to 1. When you're guessing noise, when you're guessing any sort of, random variable, basically the average of the guessing is dominated by these really unlikely cases. Think of password guessing, right? People can crack passwords by cracking passwords quickly, and then there's some passwords that are going to take years, millennia to guess, right? Those dominate the average, but they don't of the time it takes to actually guess that password. But that's not really what you're interested in. So again, that H1/2 that is in the cutoff rate, the 1 minus H1/2 for the binary case, which again, I'm going more in detail in this next set of lectures, that is actually not the most interesting thing for us, because I'm not really interested in the noise. So I'm only interested in guessing the noise with high probability, and guessing the actual noise would take me would make that mean go way up because of these very unlikely events. That's a good question. Next was, what is the average behind the average guess word 2 to the nh1/2 being higher than average guess word for decoding high probability? The some noise patterns dominate the average. Exactly, very closely related to the last question. Exactly what I'm covering in this next set of lectures. So if you're already thinking all the way into any entropy of order 1/2, come to this next lecture and it will be answered. How will Grant handle erasures? You don't actually need to do much for decoding erasures. All you need to do is just get enough degrees of freedom and do Gaussian inversion. So decoding for erasures was always very easy. Decoding for errors was what people didn't quite know how to do. Decoding for erasures is super easy. Okay, I have a couple questions here. Are structured codes like LDPC or polar codes known to be provably capacity achieving using GRAND? How the complexity scale for these codes? So actually, I will show you a lot of decoding for polar codes if you come to the last lecture. GRAND gives you maximum likelihood decoding. Okay, so if the code was capacity achieving, then GRAND will be capacity achieving. GRAND is capacity achieving if the code is capacity achieving. GRAND is a decoder, it's not an encoder. The decoding complexity for polar codes is very good. We're actually currently working on LDPC, so I don't have numbers to show you for that, but I will show you for polar codes. Actually, I believe I showed you already the chip. The chip is already handling polar codes and does so very well. As you saw, our chip, in though it's universal, has the lowest latency on record. So I don't know if people have already watched the chip part. Rajesh, do you know?
I'm not sure.
Okay, but you can watch it and you will see that the
Yes, we have seen it. We have seen
Okay.
We saw the
Yeah.
chip picture.
Yeah.
But typically, sequential decoding has a longer delay, right? You are doing guessing, then followed
No. Oh, no. Our delay is the best of any, even of all the code, even of all the decoders that are for specific.
Something you have written that the last in the latency column was left blank. You mentioned something that
That's not ours. That's not ours.
Oh, okay, that was not okay.
Ours is the one. Yeah, that one is because that was not an actual chip. We're not the last. So another group from McGill. So people in. It's funny. People in information theory has been a on this, but people in the practical side, on the chip side, have been very quick to pick up on this because they see right away that this is massively practical.
Right.
So that last column was a proposed chip implementation that just came out at ICASP by a group at McGill, Gross's group. You may know of them because they're the ones who actually made the CA Polo codes really decodable. So it's the people who really sort of got Polo codes into the 5G standard. So that was their work. Our work is, but their work didn't have delays because it's a proposed implementation. Our work is an actual chip. So if you see, we're the first column, we have the lowest delay of any of the others. So it is much shorter, and we're using, we show Polo codes. Well, we show all codes, including RLCs. From the lecture, complexity plays an important role. It's a function of noise, but not with code rate. How I can correlate with code length along with modulation schemes using Polo codes? How can I correlate with code length? Yes, so actually, if you're using Polo codes, you should, Polo codes you can use with heart detection. Again, that's what our chip does. If you want to look with soft detection, again, come to the last lecture and then I'll show you that. Just to confirm, are we fixing the random linear code at the beginning? Yes, and are some random linear codes better than other random? Okay, yes and no. Our chip is able to take codes. You can change the code on the fly. Okay, so that's one of the things because it's universal. You can change it, and actually, the chip is not for a particular code. So any codes, it's the same chip that did random linear, polar, BCH, Reed-Muller, anything. Just stick it in there. It's just a code. It's just a matrix. You can just check any matrix. Are we fixing, okay, are some random linear codes better than others? We thought that some random linear codes were going to be much better than others. And actually, pretty much, so the random linear codes I showed you, and I will show you some more in the lectures, those were the first ones picked out of a hat, and they all did really well. The fact that those outperform Polo codes routinely, it's because people were building the code and then building the decoder. Now we have a maximum likelihood decoder. And remember, we have a chip. So the thing is, they really do very well. You really have to go out of your way to find a bad linear code. We were surprised, honestly surprised. We thought that we had already suggested doing code mining and looking for good codes. You have to code mine for bad codes. You really do. But of course, that's not as motivating. Okay, so I think I've gone over all the Q&A.
May I add another question, a follow-up question?
Oh, sure. Although I do have to dash off because I think we had a half hour. Yes, go ahead.
Last question.
Yes.
So since in the continuous case, we actually guess in terms of the noise effect, perhaps the code's goodness could come into the picture in the discrete case as well. If you think of it in terms of noise effect, maybe good codes, we might be able to use the noise effect to zoom into the correct one a little faster.
You think so, but pretty much everything, a CRC seems to do better than the best known codes.
Mm-hmm. I see.
So
there is some theory to build there. So then.
this is not good news for code construction, because it, like I said, we were surprised. We were really surprised. And like I said, the uptake on the information theory side has been a bit slow. The practitioner gone off with this. So I think as information theory, actually, we should sort of catch up, because otherwise they're gonna make us look bad. All right.
Okay,
Thank you guys.
We will quickly take a picture. So I'm just, what I did was.
Oh, geez, I would have.
These are some of the participants who actually asked questions.
Oh,
So
okay, great.
So these are some of the
Thank you.
participants who asked questions. So I'm just putting them, and then maybe volunteers can take the screenshot. Okay. Thank you.
And I'll be back in a couple of days with more of your questions and maybe some answers to them. But these were excellent questions. Thank you for listening, and thank you for listening so carefully and asking such great questions.
Thank you.
Thank you.
Thanks. Bye-bye.
Bye.
Bye.